Hello everyone and welcome back to ENL 582, Modeling and Control of Electric Machines and Drives. And that is the tutorial number 2. And we will be using this to solve problems about DC machines. So in the first one we just solved a problem about the very simple kind of a DC machine. But now we will be more concerned about the modeling of the typical DC machines. We'll try to solve two extended problems, in order to just solid our concepts we have theoretically through the lectures. Let's now try to solve numerical examples about it to just make sure we understand these concepts well before just leaving DC machines behind and start talking about the more important machines, the synchronous machines and the induction machines, starting very next lecture. So in this problem, and you will find this as a solved example on Dr. Knight's online material. I provided you the link on your D2L page. You can refer to it. So it says that for a separately excited machine, so we studied that we have three different connections for the armature and field winding in a DC machine. It's separately excited, shunt excited, and series excited. Each and every one of them has some unique characteristics, and we talked about them in much detail with all the derivations for the related equations we will need while trying to modeling these kind of machines. So this problem is saying a separately excited DC motor is rotated at 1000 RPM, and that's important to keep in mind. He's giving you the speed that the motor is working at. So when you try and solve anything about a DC machine, make sure you understand what's happening with all the information is provided, because each of these information will mean something else when you try to solve these. So number one, we're just trying to know what kind of connection we have, so that's the separately excited. And if it is given, if there's a motor or a generator, that's a good information. So he's just giving you that's a motor with separately excitation, and it's rated at a speed of 1000 RPM. RPM means the revolution per minute in your note. So this revolution per minute. Okay, so that is what we give it, this simple in RPM. And the variation of armature terminal voltage, the terminal voltage of armature, and again that is the terminal voltage of armature, as a function of field current is measured under open circuit conditions in this table. So he's doing what we call the open circuit test. That means he's leaving the armature terminals open circuited, not connecting it to anything. Okay, and changing the field current by controlling the field circuit, even changing the, because that's a separately excited, so you have a separate source for the field winding. So by just controlling the voltage of the DC source connected to the field winding, you can control the current, or keeping the voltage constant and having an adjustable resistance in series with the field winding and control its value to control the field. Okay, so you will leave the armature terminals open circuited, not connected to anything, just connected to a voltmeter to measure the voltage, and change the field current and just record these values, the field current here in amperes and the terminal voltage at open circuit. So VT, that's V terminal, OC means open circuit, and just given this here. That's a very important test we'll be doing for all kind of machines we'll be dealing with. We call it the open circuit test. Okay, so it just gives you the relationship between the field current and the voltage that will be induced in the armature. Okay, the field winding is supplied with a constant voltage VF 24 volts, and that's good. He's giving you, so you have a voltage source attached to the field winding with a constant value 24 volts. Okay, and the field resistance is adjustable, so that's the idea. Here he's just providing a constant voltage to the field winding and having an adjustable resistance connected to the field winding, and just playing with it to change the value for the field current. The armature winding resistance RA is 0.2 ohms, so that's RA 0.2 ohms. Again, make sure you have a good look at all the numbers you just encounter. So that's the armature resistance 0.2. It's fairly small, and that should be. At the last lecture we talked about that the RA represents the copper losses on the armature winding, and it has to be small, otherwise that means it's a poor design for the machine. And the armature terminal voltage VT is 130 volts, so that's also a constant value used. Friction and windage losses can be neglected, and that's good. So PFW, the mechanical losses, the friction and windage losses, can be neglected, so it's 0. Okay. What needs now? A, calculate the field current if the motor is operated with no load at 1000 RPM. Okay, so he's keeping the same value of the speed he's doing now is 1000 RPMs, the same value of the speed where this table has been taken. So make sure to have this in mind. This table values has been taken at this speed, 1000 RPMs. Yeah. So calculate the field current IF if the motor is operated with no load. Okay, so that's no load condition at 1000 RPM. So at this condition where this table has been taken. Okay, so we need to calculate the field current. Easy enough. You have the table that represents the relationship between the field current and the open circuit voltage. Okay, at 1000 RPM. So if you know the value for this voltage now, you can easily find IF. Okay, guys? So that's the whole point of this. So that is the idea. So he's performing or just giving you an open circuit test. Okay, and the open circuit test is doing just like I said, is you have RF here. So he have RF and have some sort of adjustable resistance that can control to just control this. VF is constant, is giving you the effective value. So by changing our adjustable, you basically changing the value of IF. Okay, and here is your armature circuit. Okay, that is the induced voltage EA. And now here's the point. It's open circuit, means we're not connecting a load here or anything, or because we're talking about a motor, we're not connecting a supply or anything. That's open circuit here. Okay, rather he's just having here a sort of a voltmeter just to measure the voltage here. Okay, so that is the terminal voltage. Yeah, but knowing that that's open circuit, so there is no current moving here. The armature current equals 0. There is no current. That means there is no voltage drop over the armature resistance. So at case of open circuit, that means the V terminal in case of open circuit equals directly EA, because don't have any current moving in the circuit, so there is no drop over the armature resistance. So the terminal voltage in case of open circuit is the same like the induced voltage. It's the same thing. Okay, guys? And he's just using this condition, changing IF, and with a change in IF, the induced voltage changes, because changing IF changes the field, and you know that EA equals K phi omega M. So if you change IF, this changes the flux, and changing the flux changes the induced voltage. Okay, and in this case, the induced voltage directly equals the terminal voltage because it's an open circuit case. So that's how he got this table. Okay, guys? So what he's trying to do is just like this. You have here this table, which you can convert it into graph like that. IF versus the induced voltage, which equal the terminal voltage at open circuit. It's the same thing. Okay, if we try to plot it, it will look something like that, linear, and just go into saturation. Remember this same curve we talked about, the relationship between the IF and the flux density. Okay, because EA is basically constant times the flux times the speed. If the speed is constant, they will look like the same. Okay, guys? So this thing is just plotted at a certain speed. So that is 1000 RPM speed, like he said. Okay, guys? If you just play with the speed, you will have a different stuff. So if you just reduce speed, it will give you another curve like this. If you increase the speed, you will have a curve like this. Okay, so you have different curves for different speeds, and that makes sense because just you use these equations to solve it. Okay, so the whole point is just EA is directly related to phi. K is constant all the time, but you have to keep omega m, which is the speed, constant also. And just like this, you change the flux and record the induced voltage. Okay, so if you change the value for the speed, you basically changing the curve. Okay, so number A, he's just giving you that the speed is 1000 RPM. Okay, and he just saying we are still at no load. Okay, and he wants you to find him the field current. That is the demand. Okay, so let's translate everything in this. No load means the load torque equals 0. Like we said before, when the load torque equals 0, the motor torque will almost equal 0. Okay, and while the motor torque equals 0, that means the armature current equals 0, because if you remember, the motor torque equals K phi IA. Okay, so while you still have a flux in the machine and everything, because you have flux all the time, you have a constant voltage supplying the flux to the separately excited field winding. Yeah, so to get a torque equals 0 means the armature's current equals 0. Okay, and when IA equals 0, that is the same idea as the open circuit. Yeah, so that means the induced voltage now will equal the terminal voltage, because that is just the same like open circuit, because the armature current equals 0, like we said here. There's no armature current moving, that means it's an open circuit case. Okay, guys, so that's the whole point of this. The induced voltage will equal the terminal voltage at open circuit. The terminal voltage is given to be 130 volts. It's given here. Terminal voltage is just 130 volts. So the induced voltage will equal this value, because that's an open circuit case, so it's 130 volts. So you have the terminal voltage open circuit, which is EA, so simply go to the table. That is the table here, and just try to find this value, 130 volts of the T, so it's corresponding to a field current of 0.7. So the field current simply is 0.7 amps. Why we use this table? Because make sure to understand this, that 1000 RPM, that is the same speed where this table has been taken at, remember? We said this because, like I said here, this relationship related to the speed. So if the speed changes, these values in the table are no longer valid, because they are taken at a speed of 1000 RPMs. But because the number A, he's saying find me the field current at 1000 RPM, which is the same speed where this values in the table has been taken, that's fine to use these values directly. Okay, guys? Nice. Then let's jump to number B. The B saying the motor drives a load at 1200 RPMs. Now it's not at no load anymore. It had a load. Okay, and this load is now working at a different speed. It's 1200 RPMs. Calculate the armature voltage at 1200 RPM if the field resistance is 60 ohms. It's now giving you a value for the field resistance. You know it's changing because it's changing the field resistance by adjusting the resistance attached to it. So he's giving you an information about the current state of the circuit. That is the field resistance now 60 ohms, and the speed is 1200 RPMs, and he wants you to find him the armature voltage. Let's try to find this at light of what we have. So number B, the given now at the N RPMs now is 1200 RPMs. Be patient and keep that in mind. It's a different speed than the 1000 RPM value where your table has been taken. That means you cannot use the table given directly because it's now at a different speed. Okay? And he's saying that RF equals 60 ohms, and that's good. What he wants you to find him is basically finding him the armature voltage. Okay? He wants you to find the armature voltage. By the way, when he's saying armature voltage, that means he wants you to find EA, the induced voltage, not the terminal voltage. Okay? If he wants you to find him the terminal voltage, he will say find me the armature terminal voltage, not the armature voltage. The armature voltage alone means the armature induced voltage. Okay, guys? So we need to find EA. So let's use our information. You know that RF equals 60 ohm, he's giving it to you. And you know that the VF is 24 volts, constant, given all the time. So we can find IF because it equals VF over RF, that's Ohm's law. VF is 24 volts and RF is 60 ohms, so the current is 0.4 amps. Okay? If you take this to the table, you cannot take this to the table because the table is just taken at 1000 RPMs and your speed is 1200 RPMs. It's different. Okay? So if you plot this again like we said before, that is EA and that is IF. Yeah? That is the value of the curve at 1000 RPMs. Okay? For 1200 RPMs, you will portion it up like this. That is at 1200 RPMs. Okay, guys? So, if you have IF with a value 0.4 amps, like we just find here, you will go like this. If you go to the table, you will find this value because that's according to 1000 RPMs. But what we really need is this value according to 1200 RPMs, not the one that you can get from the table. But that sounds good. We can use just a direct relationship here. Why? Simple. You know that EA equals K phi omega M. Okay, guys? Looking at this here, it is the value of the current, 0.4. We can get this point at up 1000 RPMs, but actually we need the value at this point at 1200 RPMs. That means we're dealing at the same amount of current. That means phi is now constant between those 2 points. So that means EA, is directly proportional to the speed at the same flux, which comes from the field current. Okay, so you can basically find this easily. EA at 1000 RPM divided by EA at 1200 RPMs will equal the speed at 1000 RPMs divided by the speed at 1200 RPMs. And that's how we can get this point, because we don't have the values for the same table at 1200 RPMs. But we can use the direct relationship to find them. Okay, guys? So what do we have now? This is what we need here. The induced voltage at 1200 RPMs. So we need to calculate anything else. Those speeds can be found easily because that's the speed. We can calculate it. Okay? But let's find out EA at 1000 RPMs. Can we find EA at 1000 RPMs? Yes, from the table. You have IF equals 0.4 amps. Go to table. You will find EA at 1000 RPMs. Why? Because the table is taken at 1000 RPMs. So we can find EA at 1000 RPMs from the table. At 0.4, if you go back, it will give you 112, volts. 102 volts from the table. Okay, but that's not the value. That's the value at 1000 RPMs, and we want it at 1200 RPMs. So we'll use the same direct relationship. So 102 over EA at 1200 RPMs will equal the speed at 1000 RPMs divided by the speed at 1200 RPMs. Actually, that is omega M. Okay, that is omega M, and if you remember, as I said, omega M is basically 2 pi over 60 times the n RPM. So that's how you can just convert from the revolution per minute to omega M, which is the angular speed. You just multiply by 2 pi over 60. But they're just, when you just divide them together, those 2 pi over 60 will just cancel out from the numerator and denominator. And now you can find EA easily here. So that is EA at 1200 RPMs. Okay, and now it will be 122.4 volts. Okay, guys, I hope you understand what's happening. So here's a point. It is just the table is at a certain speed and you want to work at another speed, so you will just need to make some sort of direct relationship calculation, okay, to find these values. Okay, fine. So that's number B. Number C is saying calculate the torque for the above condition. So the same condition we've been talking about in number B. Now he wants you to calculate in the torque. Okay, so that is number C. We want to find the torque of the motor. At the same condition, that means the speed, the N RPM, 1200 RPMs, and the induced voltage equals 122.4 volts. We just calculated. We can use it now. Okay, guys? So, here's the point. How to find this torque. Okay, so here's the point. What equations we have for the torque? So the torque will equals K phi times IA. That's an equation we can use. Okay, but also if you remember, the torque also equal the converted power over omega m, which is equal EA IA over omega m. Remember, that is the very last thing we told you in the last lecture. That is the converted power, if you want to calculate it, can be calculated from the torque times omega m, or also from EA IA. Remember this equation? So from here we can find this. The torque can be calculated from EA IA divided by omega m, like this. Okay, guys? And why are we doing this? Because it will be much easier to deal with now. Because of the torque equals EA IA over omega m. Now we know EA, that is 122.4. And we know omega m, we can calculate it easily. Omega m equals 2 pi over 60 times the N RPM, which is 1200. So the only thing we need to calculate is IA, and now we can find the torque easily. Okay? How can we calculate IA? Easy enough. IA, that is the armature circuit, you know. That is EA, and that is the voltage of the terminal voltage. And here is the current, IA. So IA can be calculated easily like this. IA equals terminal voltage minus the induced voltage over RA. The terminal voltage is constant all the time, 130, minus EA, the calculated one, 122.4, divided by RA, which is given 0.2. And this will give you 38 amps. Okay, guys? So everything is known for the torque equation now, and you can just find the torque here to equal 37 Newton meters. Okay, guys? So that's how you deal with now. You just gather all the equations you had in mind for calculating something, and you just figure out how to find the missing information. Okay, guys? Okay, that was number C. Number D, maintaining the terminal voltage constant. So you have terminal voltage constant, he's not changing it all the time. The terminal equals 130 volts. The field current is adjusted until the motor is operating at steady state. Okay, just adjusting the field current. Supplying a mechanical load of 4,160 watts. Okay. What is this? The mechanical load, that means the P mechanical, which is the output power. At 450 RPMs, that's a new speed. He wants you to calculate the motor efficiency. Okay. That sounds good for now. Let's play a little bit with how to find out the efficiency. Fine. That's going back to the very last thing we had in the past lecture, which is the power flow. Okay, so because we are dealing with a motor here, I'm gonna remind you with the power flow diagram for the motor. The input power here is the electrical power getting from the supply, and this power is going to the armature, so we'll lose some power over the armature resistance. That's a copper losses. And then you also lose some power over the field resistance, because there's also a current moving there, so P over RF. The rest here will be your converted power. It will be converted to mechanical, but you should lose some of it at friction and windage losses, mechanical losses, and the rest is your output power, which is now a mechanical power. Okay guys, what is given for us now? He's giving you this mechanical power value, which is 4,160 watts. So this, you know, okay? And we need to find what? We need to find the efficiency. The efficiency eta equals P output over P input times 100 to get it as a percentage. So you already know P output, so all your goal is find P input. Okay? That's the whole point here, guys. So let's find out how to find this. So number one, B friction windage equals 0 is giving you that is assumed to be neglected. That means the output power is the same as the converted power. They're just equal because there is no friction and windage losses to lose between them. Yeah? That's a good thing to keep in mind. Okay? Fine. So let's play around. We need to find the input power. So the input power, which is basically the electrical power input, you can find it using two different approaches. Number one, to calculate it directly, because this input electrical power is basically the voltage times the current. So that is V terminal times IA plus V field times I field, because you have two sources. If you remember, I have the first source, V terminal, attached to the armature, that is EA, and this current is IA. So the power coming from this source, the electrical power coming from this source, is basically the voltage of it times the current, which is IA. And because that's a separately excited machine, you have another source here, VF, that is RF, and the current coming out of it is IF. So there is another electrical input coming from here, and to find it you just multiply VF and IF. So that is the first way to find it, just from the direct relationship or direct equations you have. The other thing, you can just basically find it from this power flow diagram we just draw here. You know this P input will basically equal the output power plus the losses, remember? So all those draws down here, we call them P loss, okay? And the input power has to meet the output power requirements plus these losses. That means the input power equals the P output plus P losses, okay? P output is given, we don't need to bother about. P losses have three kinds of them: the P over the armature resistance, the P over the field resistance, and the P friction and windage. The friction and windage equals 0, he assumes this 0. So this will equal the output power plus the copper losses in the armature. It is I armature squares times R armature, and the copper losses in the field is I field squared times R field. Okay, again this P output is known, so if you can find those guys, you should be fine. Okay, so to find P input, you have to calculate IF and IA to find it from this equation, or you need to find it from this equation, whatever it is. So you have two options to go with. Okay guys, Okay. How to find this? Let's play around with it. So the whole point now, we need to find both IF and IA in order to use any kind of equation. So you know RA, that's given. RA is known, RF is known. Or if you want to calculate from this other equation, V terminal is known and VF is known. But that means at all times you need to find IA and IF. And now you can use either equations of those to find the input power. Okay? So our goal is finding the currents. Okay? How to find the currents. Okay, let's play around. By the way, sorry. This value he's been talking about here, we don't know RF. Sorry, so you don't have RF. Why? Because RF is adjustable, guys, okay? So he didn't give you any information in number D here about this. He's just giving you the speed, the output power, okay, but he's not giving you any information about the field resistance, okay? So we cannot find field resistance. RF is not given here, just to keep in mind, okay? So anyways, we need again to find IF and IA to solve. And because RF is not given, calculating IF will not be easy, because if RF is given, IF is basically VF divided by RF, ohms law, easy. But here we don't have this, okay? So how we need to just go around it, how to find this, okay? And here the idea, okay? I will go like this. Let's write down the armature equation, armature voltage equation. V terminal equals EA plus IA RA. That is the armature equation. Okay? If you multiply both of the sides of the equation by IA, I will give you V terminal IA equals EA IA plus IA square times RA. Why I'm doing this? Because I want this to appear. EA IA, remember this value? That is the converted power. Okay? And you know that for here the converted power will equal the output power plus the P friction and windage. And the friction and windage here is equal 0. That's why I told you from here that the converted power will equal the output power, because this losses between them is 0. So P converted equals P output, which is 4160 watts. So we know this value, EAIA. Okay? And we know terminal voltage is 130, it's not changing. And we know RA, it's 0.2. So everything is known in this equation except for IA. Okay? It's a quadrature relationship in terms of the armature current. It will be 0.2 I armature square minus 130 IA plus 4160 equals 0. And you just can solve this equation. As a quadrature relationship, it will give you two values for IA. One of them will be 616 and the other value will be 33.75 amps. This we will be neglecting because it's just unrealistically high. So the armature current will be 33.75 amps. And that's how we can find the armature voltage from here, just using this trick. Okay? We use the information we have. We know here just the converted power and the output power. So we need to find them in the equation to use them, and that's how we did it. Just multiply both sides of the armature voltage equation by IA, and now you getting EAIA, which is the converted power directly. And now you can just use this relationship to find IA. Okay, guys? Then, how to find IF? We can again find IF because we don't know RF. so we need to use the table back. Okay, to calculate this value for IF, either you can use Ohm's law, VF over RF, if you know RF, but RF is not given, so we don't have other option to find IF but to use the table. But remember, this table is at 1000 RPMs, at you now working at 1450, so we cannot use the table directly again. Okay guys, so I will be finding EA at the current speed, which is 1450 RPM. How we can find this? Simply, it means V terminal minus IARA from the equation. You know everything now. V terminal is 130 minus IA is calculated to be 33.75 times RA 0.2, and this give you 123.75 volts. Okay, and again using the same thing, EA at 1450 RPMs divided by EA at 1000 RPMs, which is in the table we can access, will equal the speed 1450 divided by the speed, which is 1000. Okay, from now we know this value, which is 123.75. That means you can find EA at 1000 RPMs directly from here, and it will be 85 volts. This is the value you can go to the table with and find the corresponding field current, 0.3 amps. Okay guys, why we did this? Again, because the table is taken at 1000 RPMs and we're not working at 1000 RPMs. So you have to use this direct relationship kind of thing to find the corresponding induced voltage at 1000 RPMs, which can be used from the table to find the field current. Okay, remember I'm using the same idea, that is EA versus IF. Okay, we were working at 1450 RPMs, but the table is taken at 1000 RPMs. Okay guys, that is the same idea we'll deal with now. Sorry. So we need to find which value of I field we are working at. Okay, so what I did, we can find this value EA at 1450 from our calculation, because we know IA and we know for this value, which is 33.75, we just calculated, so we can use this equation to find EA at 1450, this point. Okay, so we can just use the direct relationship to find this value EA at 1000 RPMs, and then using both of them we can just go from this value, because this is the table you have, so you can find the corresponding IF. Okay guys, don't get confused about this. Good, now we have IF and we have calculated IA, so everything is in hand now. You can find P input, which is will be equaling V terminal times IA plus VF times IF. Everything is known now. V terminal is 130, IA is 33.75, VF is 24, and IF is 0.3. Everything is known now. You can find this value easy for P input, and the efficiency is P output over P input. P output is 4160, it's given, and the P input is just calculated now, so this give you 94.7%. okay, and keep in mind the efficiency should be, most of the times will be higher than 80% for electric machines. So if you just working around this, that means that's a more realistic option. If it's much less than this, that means this machine is poorly designed or you have a problem in the calculation. So if you calculate this efficiency and turned out to be 30% or something, most of the time you are just made a mistake. So go back and revise your option. Again, look at the values. Okay, The other thing, if you remember, seeing this value for the field current, it's very small, 0.3. Remember we talked about the separately excited machine and shunt excited machines? We making sure to find this, so we use the high number of turns for the field winding, okay, because that allows us to use very small values of the field current to get the same amount of field, because we don't want to use much energy to create the field. We need most of the energy, the electric energy, to go to the energy conversion process. Okay, guys? Okay. Okay, guys. That is the second one we've been trying to solve here. So the second one is talking about a series motor. So the first one was a separately excited machine, and the other one now is the series DC motor. Such saying a series DC motor has combined armature and field resistance of RA plus RS equals 1.2 ohms. He's now not giving you the values each alone. He's just giving a combined value for them because they are connected in series. You know this, the armature winding, the armature resistance and series field resistance. When connected to a supply of a terminal voltage of 0.48 volts at standstill, the motor develops a torque of 1500 newton meters. At standstill means that it's not moving, it's at zero speed, okay? So at zero speed, it's producing a torque of 1500 newton meters. Calculate the armature current at standstill and combined motor constant Kc. Okay, so number A wants you to find everything at standstill. Standstill means that the speed equals 0. Keep that in mind. Okay, the given information that the torque here, the torque of the motor equals 1500 newton meters. He's giving you this information, okay, and you the terminal voltage and everything, okay. He wants you to find him the armature current and the combined Kc constant, if you remember. So here's RS and RA, so you know the combined value for them, it's 1.2 ohms. And here is your induced voltage, and here is your terminal voltage, and that is the current moving through here, okay. So what we need now is calculating IA. So IA will equal from this thing VT minus EA over the combined resistance is RA plus RS, okay. We know V terminal, it's given here to be 48, so this equals 48 volts. RA plus RS is 1.2, so to find IA you need basically to find EA. That's the only unknown here, so you need to find EA here. How to find EA? It's basically equals K phi omega m for any kind of machines. Yes, it's at standstill, meaning no speed, so the speed equals 0, and that means EA equals 0. That's the standstill condition. If you remember, I talked about the starting condition of a machine. Okay, so EA equals 0, so this will equal 0 here. That means IA is basically V terminal over the resistances, which is giving you 40 amps. Okay, remember, that's very important to have. That we call the standstill current or the starting current of the machine, and we said it should be very high compared to the regular current of the machine. Okay. The other thing you're going to find is the Kc, okay? If you remember, in the series connected machine, we just find the phi to be a constant C multiplied by the armature current, IA, and that is multiplied by omega m. That is EA, okay? And it also in the torque equation, Kc times IA squared. Go back to your derivations, okay? So how to find Kc? We cannot use this equation because EA is basically equals 0. So we will be using the torque equation because he's giving you the torque here to be 1500. So from this equation, the torque equals 1500 equals Kc times Ia, which is 40, and now that's squared. Now you can find the combined constant K multiplied by C will equal now 0.9375. Okay? Make sure to understand that is a constant for the motor, okay? So you can use this value with whatever calculation, because K is constant, C is constant, so you can calculate them from any information and just keep using them all the time. They're constant just like the parameters, the resistances and all that stuff. Okay? Fine. Number B, calculate the torque when the speed is 1500 RPMs. Okay? Now, you need to find the torque if the speed is just 500 RPMs. Okay? Now we need to find the torque, and he's giving you the speed. And it's very thing to alert in your mind. He wants the torque and giving you the speed. That means you directly can use the torque speed relationship we just derived at the last of the lecture. So go back to the series motor and find the torque speed relationship directly. Omega M equals V terminal over the square root of Kc multiplied by 1 over the square root of the torque minus Ra plus Rs divided by Kc. Now the torque speed relationship of the series connected motor. Okay? You can calculate omega M easily to be 2 pi over 60 times the RPM, which is 500. Never miss this. You have to just multiply the speed by 2 pi over 60. Okay? The V terminal is given 48 volts. The Kc we calculated 0.9375. 0.9375. Ra plus Rs is 1.2. So everything is given. You can directly find the torque here to equal 0.854 Newton meter. Okay, guys? Very easy, just one equation. Number C here is calculate the output power and efficiency when operating at 500 RPMs and neglect the mechanical losses. That's good. Mechanical losses are the friction windage losses. He wants you to find him the output power and efficiency at 500 RPMs, that is the same speed we've been working at number B. So we need to find the output power and efficiency. Okay? We will be going almost the same way we did before. Okay? And the last example. So find P output and efficiency at the same speed, 500 RPMs. Considering this, the mechanical losses P friction windage equals 0. Okay, guys? So, should be the same idea we've been talking about. By the way, because we're dealing at the same 500 speed as number B, that means the same torque can be found, 0.854 Newton meter. Okay, because we just calculated at the same speed. Fine? So we can use this value also from the last calculation. Okay, guys? So we will be using the same thing we just did before. Because the friction windage losses equals 0, that means the output power equals the converted power, because the friction windage losses is just 0. Okay? And this can be calculated from the torque times the speed, omega M. Okay? The torque is 0.854 multiplied by the speed, 2 pi over 60 times 500. Keep that in mind. So that is P output, easily. So finding P output is just very easy to find here. We don't need to just go around a lot. But what about the efficiency? Again, to find the efficiency, it's P output over P input times 100. So we need to find P input. Okay? Did the same thing we just did with the last thing. P input here equals V terminal times IA. Remember, that's now a series connected machine. So you have just one source. So to find the power coming from this, you multiply the voltage by the current. Okay? In the last example, we have a separately excited machine. That means we have two sources, one for the armature and one for the field. That means P input, the electrical power input, is V terminal IA plus VFIF. but now it's a series connected. We are connecting the two winding in series for just one source, which is V terminal. And V terminal is given, so we need to find IA. How to find it? The same thing we did before. Go to the armature voltage equation. V terminal equals IA plus IA times RA plus RS. Okay? EA will equal KC times IA omega M plus IA times RA plus RS. Okay, guys? Now it's much easier. Everything for now is just known. The terminal voltage is 48 volt. KC we've calculated, it's constant, 0.9375. Omega M is 2 pi over 60 times 500. RA plus RS is 1.2. Everything is known except for IA. So from this equation you can find IA easily to be 0.955 amps. Okay? Easy enough. You can use this to find input power, V terminal IA. We know V terminal and IA, so that's V terminal 48 times IA 0.955. Okay? So you can find the efficiency easily. P output over P input times 100. We have just calculated P input and P output have been calculated here. So doing this will give you around 97%. Again, it's a good efficiency for a motor. Actually, it's a very high efficiency, and that just sounds good. Okay, guys? Again, that's the whole point. We don't have very complicated math to do on our problems, guys. We don't have very big integrals or something to just give you a headache. But it's very, very, very simple math to do, but it's not the math that matters. It's the physics. It's how to understand the engineering of everything. If you understand what's happening well, you will not find a problem solving anything. But if you don't understand what's happening and just following the math, you will always make big mistakes. So keep in mind that you understand what's happening. Everything matters. Okay? The connection of the machine, what's given, what's not given, how to use the given information to find out what's unknown, and how to use the different equations you have already derived to just find these unknowns. So please take some time to resolve these problems by yourself, and feel free to ask me any questions you want. I will be very happy to answer them on Friday's morning's meetings. Okay? Thanks so much for joining me today, and I will be seeing you next time.